Hi, we are going to talk about gravitational waves, its precedents, about some tensors, formal definition, sources, detections, and some applications.
In this section, we will talk about the precedence of gravitational waves. Our story goes back to the 18th century, when it was the height of Newton's theory of universal gravitation. However, there were several causes that prolonged their study. The first to question the eternal universe was Edmund Halley, reviewing eclipse records and noticing a secular longitudinal acceleration of the moon. This statement was later studied by Laplace, who present four postulates from which the Laplace effect was concluded. Even in the 19th century, thanks to the Newtonian theory, the planet Neptune was found. However, the theory has flaws in accurately describing the trajectory of the planet Mercury. Coming to think of the existence of the planet Vulcan at this time, such existence was never verified. In 1908, Poincaré was the first to use the term of gravitational waves under the influence of Maxwell's electromagnetic theory. Later, in 1938, Howard Percy Robertson, an Einstein collaborator, corrected the path of Mercury using the theory of general relativity. Before this happened, it is important to highlight the work of Max Abraham, Einstein's rival, questioning general relativity and presenting counter-arguments based on the unification of gravity and electromagnetism. It was the first to say that it was not possible to find a gravitational radiation dipole. After Einstein's publication, various efforts were made by various famous physicists to verify the existence of gravitational waves, from Feynman's statements to Weber experiments without obtaining any evidence. It was not until 2015 when the first gravitational wave was detected, and in 2017 it was made public. The first detection of gravitational waves was in 2015 and was published in 2017 by the Liu. A tensor is an algebraic object that describes a multilinear relationship between sets of algebra objects related to a vector space. These algebra objects are covectors and vectors. If we see in a graphical version, look at a box, a vector of type 0n.
Now we can start with the definition of the gravitational waves. The gravitational waves are a consequence of the theory of relativity created by Albert Einstein. This theory takes the gravity as a distortion of space and time, and the space and time as a kind of fabric. In the right side, we can see the Einstein's field equation that describes all this theory in a tensorial form. The G tensor is related with the space and time and its curvature, and the T tensor is related with mass and energy. Now, the gravitational waves are a kind of ripples that travel through space and time and are caused by massive objects that are accelerating. They exist many kind of sources. For example, two black holes orbiting each other. Now, if we want to have a more formal and mathematical definition of gravitational waves, we should start with the Einstein field equations, more precisely with the weak field equation that is similar to the first one, but in this case we are far away from the source. And we could remember what the Allenberg operator is, and it appears on the screen. And if we want to make it simpler, we should take it as in vacuum. So we make the T tensor related with mass and energy equals 0. Now we get this equation that is a tensorial form of the wave equation. And if we solve it, we get this expression that is really similar to other expressions for the plane waves. So there is where the definition of a gravitational wave come from. Now we see a small simulation created by LIGO that was the team that first detect this kind of waves. We see that are two black holes that are accelerating in a circular movement, and they create this kind of ripples through the fabric of space and time. And we will continue analyzing this in the next part of the video.
Now, in this section, we are going to talk about sources of gravitational waves. Every massive object that accelerates produces a gravitational wave. That includes humans, cars, and planes. However, this is not as easy as it seems. In our planet, the masses of the objects are far too small to be able to produce gravitational waves big enough to be detected with the more advanced instruments. To find a detection, we should go outside our solar system. In the universe are a lot of massive objects such as stars and black holes big enough to produce gravitational waves that can be detected. The continuous gravitational waves that are thought are made by a very massive star with single spinning, for example, a neutron star, like in the video. If the spin of the massive objects stays constant, the gravitational wave stays constant too. Every single change of the circular movement will be detected as a change on the gravitational wave it emits. The next class of gravitational waves are called compact binary in spiral. As its name says, this kind of gravitational waves are made by a very dense compact binary system, and at the same time, this class has three different categories: binary neutron stars, binary black hole, and a combination of the two, binary neutron black hole. Each category has a unique pattern of gravitational wave, but all three generate the same mechanisms of gravitational waves. However, we do presume that many small gravitational waves are passing by from all over the universe all the time, and that they are mixed together at random. These small waves from every direction are called the stochastic signal. This will be the smallest and most difficult gravitational waves to detect, but it is possible that at least part of this stochastic signal may originate from the Big Bang. Detecting gravitational waves from the Big Bang will allow us to see further back into the history of the universe.
In order to detect gravitational waves, you need to take in consideration that the wave will interact with matter and will compress an object in one direction and will stretch them in the perpendicular direction. So you can create the detectors uh, with that information to see if you have detected the gravitational wave. Some of the first gravitational wave detectors were the resonant mass antenna, which is basically a large solid body of metal that is isolated from the outside vibrations in order for it to resonate with the vibration of the gravitational wave. And the most famous detectors are the ones that use interferometry. They are all around the world. We have Virgo in Italy, Geo in Germany, TAM in Japan, and LIGO in the United States. The most recent uh, achievement of these detectors were made by LIGO and Virgo in a collaboration. They were the first one to detect gravitational waves, which earned them the Nobel Prize. They use Michelson interferometers, and these are interferometers that are really sensitive to perturbations. So they have a laser beam that is divided into two and then is recombined to form an interference pattern. For example, we have LIGO, which is about 4 kilometers in length, each arm. So they are really big in order to detect the small gravitational perturbance, which are in the range of 10 to the minus 18 meters. The problem with the sensitivity is that they will receive a lot of noise because they will perceive the passing trucks, lightning strikes, earthquake. So in order to reduce this noise, the interferometers have, well, a lot of advanced technology, but they also use the information of different detectors in different areas. So if a gravitational wave passes, the detectors will receive the same information with a small time difference, and they will be able to discharge the noise.
Now that we know what gravitational waves are and how to detect them, let's talk about the applications and why they are really important. The first impact that we have is in astronomy. Think it this way. With the help of telescopes, we can see the universe, but with gravitational waves, we can hear it. And with this, we have an ability to detect a different kind of information. We know that light comes in different manners, such as X-rays, gamma rays, visible light, and radio waves. But what happens if we want to look for something that doesn't radiate light? Black holes are known because they have such a strong gravitational pull that even light can get away from them. As a result, they're typically represented in images and illustrations as big black spheres. They do not emit light and they do not radiate light. There are other ways to see black holes. For example, the material around it radiate light, and with it we can know its silhouette. But for LIGO, that cannot happen because they're normally between 10 and 100 times the mass of the Sun. And of course, there's no material around it, and they're kind of invisible, but not for a gravitational wave detector. So LIGO can see things that no other observatory can, and that's a big reason why people are calling this the beginning of something new, and even know what happened when the Big Bang occurred.